So I wasn't, first of all, I'm definitely more on the engineering side, so it was actually really fabulous that we get to see so many different perspectives on what's in this school. But when I was originally thinking of this title, I wasn't really thinking of a TED Talk. And so, let's see, here's the thing here. And so perhaps a better, more TED-esque style of title would be Mitigating Hazards in a Flat World. And actually, this particular title is very meaningful to me. So I actually, in 2009, was an undergraduate research student that was funded by the National Science Foundation. And as part of that work, I got to visit the University of Illinois for a summer, and I was engaged in earthquake engineering research. And if it hadn't been for that opportunity, I would have never gone to grad school, and I would not be here today. So it was really a pretty pivotal moment in my career. And I still remember the email at Simpson7007@AOL.com. That they were going to send me to Hawaii, and I thought it was a scam. So this was me in 2009. And as part of this conference that was originally part of the NSF work that I was doing, they flew students from all over the United States to meet and talk about earthquake engineering. And I have to admit that I was hooked. And so the title of that conference was Seismic Mitigation in a Flat World. And every single job application that I've applied to, including this one, that's been in my application. It was incredibly inspirational to me. And in fact, when I look at a lot of my research endeavors, I think about what it means to have mitigation in a flat world. And so if you look at the research that I do, when I think about a flat world, I think about how we globally need to address more and more extreme natural hazards and climate change. I think about how our students need to become very comfortable with practical, sustainable, and more resilient technologies. And then this last piece, I think, is actually incredibly critical, and it is that to really solve complex problems, we can't do them by ourselves anymore. And so we really need to borrow and transfer ideas from other knowledge domains, and we as a community also need to value collaboration, knowledge exchange, and diverse experiences. And so I sort of set up my talk based on those three things, keeping in mind the mitigation of flat world. And I can't talk to you about all my projects, so I've just chosen a few. So let's start with that first one, which is this idea of globally addressing climate change as well as natural hazards through our built environment, which is really where we live and work. It has a huge impact on our community. And to give you an example, traditionally, when we design buildings, we design them for life safety and collapse prevention. But that's really not enough. And a good example of why that's not enough is when you look at it in terms of a community and how it's resilient to natural hazards. So this is after the 2010 to 2011 Christchurch earthquake sequence in New Zealand. And these buildings did not experience collapse like you saw in the previous video. In fact, they were designed as intended, which is to mitigate collapse and protect its occupants. And this is about 10 years later when I was there in 2018. And you can see that although they protected the occupants, the majority of the building stock was torn down. This has a huge repercussion when it comes to the community, and Christchurch still hasn't recovered, and it's now 15 or so years later. And so a huge part of structural engineering and a huge effort by our community is to think a bigger picture than just damage and collapse and start thinking about what those community metrics might mean so that we can ultimately make more value-informed and cost-informed decisions about how we build and how we design. And so typically, this has been in terms of 3Ds, death, dollars, downtime, but apparently that was too negative. So more recently, it's been thought of in terms of the 3 S's, which is safety, sustainability, and serviceability, which is kind of interesting. But really, it's what happens if you, as the building owner, have a building that is damaged, and how much damage are you willing to handle in terms of downtime, initial upfront costs, but also post-event repair costs. Potentially you think about carbon impact, and then that casualties and unsafe placarding is still in there, but it's mixed with a whole bunch of other metrics. And so how my group has started to think about this is, well, now you have multiple objectives, and you might want to meet ones or others depending on what performance you want for your system. And so potentially you might have resiliency objectives that are associated with what happens after an extreme event. So perhaps for a very, very rare event, if you're Apple or Google, you actually don't want to shut down. Or perhaps if you're an educational facility or a hospital, the community can't afford to have you shut down. So those are what we're going to call resiliency objectives. And then perhaps you also have sustainability objectives that go into the materials and how you actually build and construct the initial building itself. It could also go into what happens in terms of post-event repairs. But if you're going to design for all of these objectives, perhaps what you also need is a new building system. And so what my group thinks a lot about is how do you start mix and matching traditional building materials and components so that the designer and the building owner can actually target the performance of their building based on what they want, based on multiple selection criteria. So what you see on the right there is a 6-story building that we tested in January last year. And so what you're going to see is that there's the largest shake table in the United States is at UC San Diego. And so my group designed and built this for sort of first-of-its-kind building. We shook it 23 times with earthquakes that are pretty severe. And this building was totally reoccupiable after the event. So very minimal damage, very superficial. And so that's part of the work my team does. But let's look at this second piece, which is sort of looking at technology. And to do this, we've sort of rethought traditional structural engineering, which is mostly focused on urban environments, and looked more at mechanical type systems associated with renewable energy devices. And so this is a little bit outdated, but I think drives an important point home. So natural disasters are disasters that by definition have an extreme impact on communities. And so in 2023, 399 events were labeled as disasters. And if you look at that number, it's 369 over a 20-year span from 2003 to 2022. What's really interesting about it is you see the wildfire there. That was actually the fire in Hawaii. That was one of the top 10 most expensive disasters, mostly because it was in the United States. And then the earthquake there, that was the one associated with the most number of casualties in 2023. That was the earthquake in Turkey. The big blue dots are associated with events related to climate change. So my group, what we've been thinking a lot about is how do we expand not just on natural disasters, but also thinking about climate change itself. And so, again, we're structural engineers, so we focus on things that have mechanical type behavior that we're very familiar with from the built environment. And so we've been doing a lot of work on marine energy devices. And these are very interesting devices because they promise some mitigation measure against climate change. But the issue with them is that they're extremely difficult systems to simulate. There's a lot of multi-physical phenomena that are happening that affect these wind turbines. And if you're building off the coast, the Pacific coast of the United States, the water is actually fairly deep, and so they have to be floating. And so you need to be able to simulate not only dynamics associated with the rotor moving, but also aerodynamics associated with the wind, the structure itself, the hydrodynamics of a floating system, as well as mooring lines that could be anywhere from 1,000 to 2,000 meters deep, and the associated anchorage and soil structure effects associated with them. And these are all typically thought of as different knowledge domains. So there's not a single person who usually does all of these at once. I think the worst part about this is not so much the multi-dynamical nature of these systems, but that they're so incredibly large. So these will be the largest rotating machines ever constructed, and they are going to be floating in the Pacific Ocean. And so, this is just an example. This is probably about a 1 megawatt device. So the expectation is that California will be building 10 megawatt devices. Those are the size of the Eiffel Tower. So incredibly large devices, and that, coupled with the multi-physics nature of them, makes them very, very hard to simulate in terms of controlled laboratory testing environments. And so what my group has sought to do is, well, what if we could sort of separate out the physics and study a portion of it numerically, and a portion of it physically in an experimental setting. And so what we do is we take a system and we break it up into pieces where we're able to house and partition the domain depending on the governing equations that we're interested in. And then we use actuators and sensors that actually inform the numerical model and the physical model in real time. And so this is what that looks like. So we would have a numerical model, say, of the wind that's interacting with a physical small-scale experiment of the wind turbine in a wave basin. We have a motion tracking system that monitors the motion and feeds that to update the wind loading. And then we have a 6 degree of freedom robotic manipulator that then applies that force resulting from the numerical model in the wave basin itself. And so by doing this, we can sort of separate out the different physics, but then we can also get the interacting component. And so some of you might have looked at that and been like, that looks really hard. And it really is. There's a number of complexities to it. One is just the diversity of the different domains that you need to have involved. But another is the fact that it has to be in real time. So as much as I would love to slow down the fluid flow, I actually have to have my actuation and numerical models keep up with what's happening in the physical experiment. And so my team develops a lot of different hardware architectures, including fiber optic communication and shared memory networks, as well as different softwares to reduce the computational time of the numerical model and different algorithms associated with that. And so that lower right-hand picture is actually what we got funded for as part of the discovery grant process. And so this is sort of a very technical challenge that sort of feeds into that third point I was making about converging across different disciplines and sort of borrowing different ideas from other fields in order to tackle the ones in our field. But I think this is actually much bigger than just thinking about it technically, and that's that if we're really going to tackle these really massive and very complex problems, we need more people, and it needs to be incredibly collaborative. So the mass timber building and the 6-story testing that I just showed was a huge team of students and researchers as well as practitioners. This is only half the team that was involved in that project, and that project wouldn't have been possible without this many people. And then if you think about sort of doing these interdisciplinary type settings, the number of expertise involved makes that team ever more critical. And so in this third piece, I think just coming back to the flat world and thinking about what this means for our students, the next generation of problems and engineers, I sort of borrowed a figure that I think makes sense to me in terms of this flat world principle. So we're going to put the engineer's time on the y-axis, and then we're going to put these sort of different bins that we expect our students to sort of have expertise in by the time that they graduate. So concept, creativity, and innovation, design and analysis, interpersonal communication and engagement. And in the past and up to right now, it sort of looked like a frowny face, where because of the existing tools, we spent a lot of time on design and analysis. But as technology grows, and as teamwork becomes more and more critical, perhaps we need to be thinking about the education of our students a little bit differently as we think about the new problems that they're going to have to address. And so perhaps it becomes a little bit more like a smiley face as we start thinking about the tools they need to actually be successful. And so I'll just end with this last slide that a lot of my work has to do with thinking about this next generation of students. And these are a number of visiting scholars that come through my lab, as well as my own students, as well as the different US students that we've collaborated with at other institutions. And I just think this is a great slide to end on because I think this is really who we're trying to address. Okay, thank you.